Welcome to my channel. Today we're going to explore one of the most fascinating questions in artificial intelligence. Is human data a gold mine or a cage? When we train AI systems on human-generated data, are we giving them a treasure trove of wisdom, or are we inadvertently trapping them within the limits of human capability? This question lies at the heart of a remarkable story in AI history, one that completely changed how we think about machine learning and the role of human expertise in training intelligent systems. The answer, as we'll discover, reveals something profound about the nature of learning itself. Let's start with how we traditionally train AI systems. In supervised learning, the standard approach, we follow a simple pattern. Human experts generate data. That data is collected and curated, and then we use it to train our AI models. The model learns by studying examples created by humans, essentially trying to mimic their decisions and patterns. Think of it like an apprentice learning from a master craftsman. The apprentice watches, imitates, and gradually becomes skilled. But here's the crucial limitation that's often overlooked. The apprentice can only be as good as the data they learn from. If the teacher has blind spots, the student inherits those blind spots. If the teacher never explored certain strategies, the student won't either. This fundamental constraint sets up everything we're about to explore. This brings us to AlphaGo, DeepMind's groundbreaking AI that took on the ancient game of Go. AlphaGo was trained using this exact supervised learning approach. The team fed it over 30 million game positions from 160,000 professional human games. Think about that number for a moment. Centuries of accumulated human wisdom about Go distilled into training data. AlphaGo studied how the greatest human masters approached the game, learning their opening strategies, their middle game tactics, and their endgame techniques. The result was remarkable. AlphaGo became world-class, capable of defeating professional players. It seemed like proof that the human knowledge approach worked brilliantly. But there was something lurking beneath the surface, a limitation that wouldn't become apparent until later. Here's the problem with learning from humans. It creates a ceiling. When an AI learns exclusively from human data, it inherits not just human knowledge, but also human limitations. The AI absorbs our strategic patterns, but it also absorbs our biases. It learns the moves we make, but it cannot discover moves we never considered. Performance becomes capped at the teacher's level. The AI might approach human-level ability, it might even match the best humans, but it cannot fundamentally exceed what humans have demonstrated. It's like training to be a runner by only studying videos of other runners. You might become very good at imitating their form, but you'll never discover a completely new technique that no one has ever tried. This ceiling effect is subtle but profound, and it represents a fundamental constraint on how far supervised learning alone can take us. Now, enter AlphaZero, and this is where things get truly fascinating. AlphaZero took a radically different approach, one that philosophers might call Tabula Rasa, which means blank slate. AlphaZero started with absolutely zero human game data, none. It wasn't shown a single professional game. Instead, it was given just two things: the rules of the game, meaning which moves are legal and what constitutes a win, and the goal, which is simply to win. That's it. No openings database, no endgame tables, no strategic concepts that humans have developed over thousands of years. Just the raw rules and a simple objective. Everything else, AlphaZero would have to discover on its own through a process called self-play, where it literally plays games against itself to generate its own training data. The self-play mechanism is beautifully simple, yet incredibly powerful. AlphaZero plays games against itself, essentially having conversations with itself about what works and what doesn't. After each game, it learns from the outcome, updates its strategy, and then plays again. Over the course of training, it played 44 million games against itself, using just 4 tensor processing units over 72 hours. Watch the evolution. At hour 0, it plays randomly, making moves with no understanding. By hour 4, basic strategies emerge. By hour 24, it's playing at world-class level. And by hour 72, it has become superhuman. Each game generates new training data, creating an essentially endless supply of experience. Unlike human data, which is finite and fixed, self-play data can be generated infinitely, limited only by compute resources. This changes everything about how we think about the data bottleneck.
Perhaps no moment captures this approach better than the famous Move 37. During one of AlphaGo's games against a top human professional, it played a move that stunned the Go world. Fan Hui, the European Go champion, described it as not a human move, saying he had never seen anything like it, calling it beautiful. Human experts initially thought it was a mistake. The probability that a human player would make this move was estimated at just 1 in 10,000. It violated conventional Go wisdom that humans had developed over centuries, and yet it was the move that won the game. Without being constrained by human training data, the AI had discovered a strategy that existed in the vast space of possibilities, but that humans had simply never explored. This is what happens when you remove the ceiling of human data. The AI doesn't just match human performance, it finds entirely new territories of excellence.
Then came the ultimate test. DeepMind pitted AlphaZero, the system that learned from nothing, against AlphaGo, the system trained on 30 million human positions. The result was devastating and definitive. AlphaZero won 100 games. AlphaGo won 0. 100 to 0. Complete domination. The student without a teacher had utterly crushed the one that learned from the best human masters in history. Think about what this means. All those centuries of accumulated human Go wisdom, all those professional games, all that expert knowledge, and it wasn't just matched by self-play, it was completely overwhelmed. The approach that seemed like it would benefit from human expertise was ultimately limited by it. The approach that started with nothing but the rules discovered strategies that humans never imagined. So why exactly was human data a bottleneck? Let's break it down. When you train on human data, you're working with a limited exploration space. Humans have only explored a tiny fraction of possible strategies over thousands of years. The AI inherits human biases, playing in ways that feel natural to humans but may not be optimal, and performance is fundamentally capped at the teacher's level. Compare this to self-play. There's unlimited exploration because the AI can try any strategy, not just ones humans have used. It discovers novel approaches, moves like Move 37 that no human ever considered. And there's no performance ceiling because the AI keeps improving as long as it has compute. Human data represents a narrow slice of all possible strategies. Self-play explores the entire space. It's the difference between studying one path through a forest versus having a map of every possible route. This brings us to a fundamental paradigm shift in how we think about AI development. The old thinking was straightforward: more data equals better AI. If you want a better model, collect more training examples. This drove the race to accumulate massive datasets. But AlphaZero demonstrated a different equation. More compute can equal better AI, even without more data. When you can generate your own training data through self-play, the bottleneck shifts from data collection to computational resources. Look at the scaling curves. Data-limited approaches eventually plateau. You run out of new examples, or the examples you have don't cover enough ground. But compute-based approaches can keep climbing, generating new training signal as needed. This insight has profound implications for the future of AI research and where resources should be invested. Now here's where things get really interesting for today's AI landscape. Current large language models are trained primarily on human-generated text using next token prediction. They learn to predict what word comes next based on patterns in the training data. Sound familiar? It's the same supervised learning approach that AlphaGo used, and it faces the same ceiling. LLMs can only be as good as the reasoning present in their training data. We're seeing the evolution begin with chain-of-thought prompting, where models show their reasoning steps explicitly. The next frontier might be self-generated reasoning, where models create and verify their own reasoning chains to improve, similar to how AlphaZero generated its own training games. Can LLMs learn to self-play with reasoning the way AlphaZero did with games? This is one of the most exciting research directions in AI today. So let's bring it all together with our key takeaways. First, human data has real limits. Training exclusively on human examples creates a ceiling where the AI can only learn what humans have demonstrated. Second, self-play can break through those ceilings. AlphaZero proved definitively that self-generated data through reinforcement learning can surpass any human teacher. Third, and perhaps most practically, the future is likely hybrid. The most powerful AI systems will probably combine human knowledge for bootstrapping and direction with self-improvement mechanisms for breaking through limitations. So, is human data a goldmine or a cage? The answer is actually both. Human data is incredibly valuable for getting started, for bootstrapping an AI system to a competent level quickly, but it shouldn't be the final limit. The path to truly superhuman AI may require eventually transcending the data that humans can provide. If you found this exploration helpful, please like and subscribe to the channel for more AI engineering content. Thanks for watching.